We have previously said that mass is the same as inertia, or laziness, how hard it is to get an object to change its motion. In this lab, I'm hoping you'll get a feel for that. You're going to have a variety of masses and a hanging spring. If we put a mass, say a 100-gram mass on a spring, give it a gentle little tug, it bobs up and down with a certain period, a certain amount of time it takes to go back and forth. Check out what happens if I make the mass larger. We'll say 500 grams. Give it the same tug. It takes a lot longer. The 500 grams is lazier. It's harder to change its motion. And it takes the spring longer to do it. So in this lab, we're going to try a big variety of combinations. And we're going to time how long it takes for a complete back and forth, which is called a period. We're going to see if there's a relationship between period and the amount of mass that we're putting on here. For some masses, like this 50 gram, it's going to be going so fast that it would be hard to start and stop our stopwatch for a single up and down. So one trick that has worked for a lot of people over the years is to count 10 up and downs and time that, and then we can divide whatever time we have by 10, and then we get a more accurate answer. We average our error out across more observations. In order to time, get your weights going up and down evenly. You don't want them jerking violently. Grab a stopwatch. You can use your phone if you want. And what you're going to do is when the weight gets to the very bottom, say 0. And then each time it gets to the bottom again, count up until you get to 10. For the faster ones, you're going to want to do this in your head because you won't have time to say it. But you're going to start the watch on 0 and stop it on 10. So you're going to get the value for 10 up and downs. So here we go. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got 5.93, and that is 300 grams going up and down. So for 10 periods for 300 grams, I'm going to put 5.93. I don't have every value between 50 and 1,000 here. I just have the ones I can make with this set of weights that I got. But I'm going to go through and get all this data now, and then we'll graph it. So here is 50 grams. Here's 150 grams. Here is 250 grams. Here's 350 grams. Here's 600 grams. Here's 600 grams. So here's our data. So we're just going to divide by 10 to get all of these. So that's pretty simple. You just have to move the decimal place 1 to the left. So this would be 1.086, 1.014, etc. 0.987. So I'm sitting here with the data that we collected from the mass bobbing up and down. And as you can see, we have various masses. We have the time it took for the 10 periods we watched, and then the time for each individual period. And I've gone ahead and copied that over to a spreadsheet. I didn't copy the 10 periods, I just copied the 1 period. And I also converted our mass to kilograms, because if we're going to come up with equations, we want to use the standard units. So the next thing to do is just to have Google Sheets graph it for us. So we'll select all the data, insert chart, and it is a scatter plot. And that's it. So series, which is the y-axis is mass and the x-axis is period. So we should probably label that just so we don't confuse ourselves. So the vertical axis title was mass in kilograms, and the horizontal was period in seconds. And that's it. So what we need to do now is kind of see what trend line fits this the best. So if we start fitting a trend line, our first option is linear. And you can see that it's pretty close. If this is actually the true pattern, then the relationship between mass and period can be written like this. We could say that mass is proportional to period. That little squiggle in the middle means proportional. So this is just saying as period gets bigger, so does mass. And that's a definite possibility. The only thing that leaves me a little concerned is that at this end of it, the points are above the line. At this end, the points are above the line. And they kind of bow under the line in the middle. And that's often what happens when you have a curve. So would there be a better fit to this? Let's try parabolic. So polynomial of degree 2. You can see it's a much better fit, but it's not a huge difference. So it's really tough to determine between them. Usually, you don't want to make the equation more complicated than the data justifies. So what we'd be claiming if this one was true was that mass was not proportional to period, but mass was proportional to period squared. So you don't typically want to make it more complicated than you have a physical reason to justify. So I would say with this data, you don't have a strong case either way. We'll do some math later on where we'll derive what this relationship is, and we'll see that in fact it is a parabola. And our data does seem to bear that out. If we had masses that were significantly less than the ones we have and significantly more, the curvature would become more clear. So at the end of the day, we did this lab to show that mass was proportional to period, either period or period squared. And the reason that's important is because if something is going back and forth with a very short period, that means it's relatively easy to change its motion. If it's going back and forth with a long period, that means it's harder to change its motion. And that gives us a good idea of what mass is. It's a measure of how hard your motion is to change.